Yeah, good morning, good afternoon, good evening, good night, wherever you are. I just checked my hard disk and I found some files from my presentations at the 1999 first Michelson Summer School. So I have been giving talks about instrumentation at several of these, including the first and including the first online. So this time instrumentation really means instrumentation for precision radial velocities. And the type of instrument that we use for that is called a cross-dispersed Echelle spectrograph. So I want to explain what that is and how it works and the fundamental limitations of observing with this type of instrument. So you probably all know gratings. A grating is essentially a regular grid of grooves or lines, and light that is reflected by this grating can interfere either constructively or destructively. So from a simple path length difference calculation, you get the so-called grating equation, which tells you that you get constructive interference in certain directions and you observe light at a given wavelength if this equation is fulfilled. You can compute the derivative of the angle to lambda, and then you get the dispersion, which is the spread of the spectrum on the detector. And then from that, you can calculate the resolution of the spectrograph, which is defined by lambda over delta lambda, where delta lambda is the difference in wavelength between two adjacent lines that you can just separate from each other. So you can see that there are two different lines and not one of them. And the equation for resolution is given here. It contains the size of the grating. It contains the size of the slit that you use or the fiber on the sky, the telescope diameter, the number of grating lines, and the diffraction order. So this equation is really driving a lot of the instrument design and the considerations for instrumentation that we use. So as we will see, getting the best possible radial velocity precision requires a relatively high resolution, typically of order 100,000, sometimes a little bit less, sometimes even more than that. Getting that kind of precision is not trivial if we look at this equation, which I have copied here from the previous view graph. So one strategy to get high resolution is to use a large diffraction order, so the small m, and a large number of lines that are illuminated, which is a large grating, or in the relation that contains the size of the grating, the W here, you see the size of the grating enters directly. You can see immediately that for the same resolution, a larger telescope requires a larger spectrograph. Also, a smaller slit on the sky allows you to build a smaller spectrograph. But if you do that, if you make the slits smaller than the seeing disk, then you use light, and you don't want to do that, of course. There is a trick in getting more light in your spectrograph for the same size, and that is so-called image slicing, in which you cut the star image into two pieces or even more and stack them in a vertical alignment. There's also an attractive alternative, and that is the use of adaptive optics. If you use adaptive optics, then the angular size is about lambda over d, and that is the optimum that you can achieve. So trying to keep your spectrograph manageable in size for a large telescope, a high resolution, that is a very important consideration. Here's the interior of one example. This is the CARMENES spectrograph that I know very well. And so you see this is a pretty large grating that is seen here. So this is typically in a visible light spectrograph. This is the most important component, the most expensive component in the spectrograph. In a near infrared spectrograph, the detectors may be even more expensive, but the size is a driving consideration. And here, this is the vacuum tank. You see, these are not small instruments. These are expensive instruments. And here are some typical parameters. So taking a wavelength in the middle of the wavelength range of this spectrograph, this is about 8,000 angstroms. This is for us the 77th order. So the grating is really used in a high order. This particular grating has 31.6 lines per millimeter. The size of the beam in the spectrograph is 15 centimeters. The tangent of the reflection angle is 4. So also this means that the length of the grating is about 4 times the beam diameter. You saw that it is rectangular. We slice in 2, so this is shown here. You cut the fiber image into 2 and you stack that vertically. So in this dimension here, which is the dispersion direction, it's only half the size. So that makes the spectrograph smaller by a factor of 2. And we are at a 3.5 meter telescope. And in the end, you get a resolution of about 94,000. So you can see from these numbers, you are pretty constrained in the construction of such instruments. You cannot really afford to make the grating larger. You cannot really afford to make the fiber on the sky smaller without losing light. And you do not really want to make a resolution lower. So we are all faced with these issues when we consider spectrographs, especially for very large telescopes. Yeah, this is only a 3.5 meter telescope. So if you want to put a similar instrument on an 8 meter telescope, on a 10 meter telescope, you would even have to make it larger or adopt a strategy in which you have more than 2 slices, or make the fiber on the sky smaller, which you may be able to afford if you're at a site that has extremely good seeing. But one can see we are pretty much in a corner of what is possible for these instruments. Another thing that one should understand about the optics is, of course, in a grating, the grating is mostly in the first place a mirror. So a normal grating sends most of the light into the 0th order, where you don't even get a real spectrum. What we are using here are so-called Echelle gratings or blazed gratings, in which the facets are tilted with respect to the main direction of the grating. That means the reflection is mostly away from the normal. In that case, you can get most of the light into the useful orders. But then this means that the efficiency also varies very strongly as a function of wavelength. This is shown here. The efficiency is good for the nominal direction in which the grating is blazed, but it drops if you go away from that specific wavelength. So for a spectrograph that is used in very high order, you get this function of the efficiency that is an oscillating function of wavelength. If you see spectra taken with this type of instrument that are nice and flat, then probably there was a step in the data reduction that took out this so-called blaze function by dividing through this function. But the signal to noise ratio always has this behavior that it is good at the center and it drops off towards the edges of the order. Also, you have different orders that are reflected into the same direction at different wavelengths. You remember in the grating equation, you have m times lambda, the product of order and wavelengths, and then on the right-hand side, some angles. So that means that, for instance, the 100th order at 5050 angstroms goes into exactly the same direction as the 101st order at 5000 angstroms, because the product is the same. So this, schematically here, this shows different orders, but in reality, they are all on top of each other. And of course, you don't want that. You don't want to observe wavelengths, different wavelengths in the same pixel of your detector. But you can turn this into an advantage, as we shall see in a minute. So the order sorting means you have to take out, you have to somehow resolve this ambiguity that different orders fall onto the same pixel. And you can do this either by just using a bandpass filter, by cutting out the desired wavelength range, but then that means that you use only a small part of the spectrum. The technique that we use, and this is what gives this type of spectrograph the name, is cross-dispersion. So we put in a second dispersing element. So here, this is schematically, here's this Echelle grating that then creates all these different orders on top of each other. Here we have a so-called cross-disperser. So this is turned by 90 degrees and introduces dispersion in the orthogonal direction. And then we get the different orders separated in the other direction. And this can be either also a grating or a prism, for instance. So the format that we get in this way is this cross-dispersed Echelle format, in which the different orders run in one direction, each one runs in one direction, and they are sorted in the other direction. And that has the nice property that you can get a very large wavelength range on a square detector. And so the raw data of these instruments always look like this. Oops. Now my computer seems to be a little bit stuck. I think I'm still on, but
yeah, we can still hear you.
I can't.
Still see you, and we see.
Yes. Okay. Now it continues. Okay. So I wanted to recommend this book, from which I also took some of the figures for looking up the basic optics. So now about the fundamental limit for getting radial velocities out of such an instrument. So the frequently asked question here is, we said we get typical spectrograph resolution of order 100,000. So if you convert this into a Doppler velocity, this is 3 kilometers per second. And as Deborah very nicely explained, we can get Doppler shifts with amplitudes of 1 meter per second, or maybe even centimeters per second out of such an instrument. So how is that possible? This doesn't look intuitive. So let's look at more detail in what it actually means to measure a line with a certain precision. Keep in mind, what we actually measure on a detector is we have pixels, and in each pixel we measure a number of counts or a number of photons. And this is the number, of course, that has an error bar associated with it. What we do next is we fit the line, say with a Gaussian or some other profile, but that fit has an error. This may also be a valid fit through those data, or this may be a valid fit through those data. Within those error bars, we cannot really tell. So we have an associated measurement uncertainty that I call small delta x. Now, if you repeat the same measurement, the same line, and we have higher signal to noise, smaller error bars, Again, we do the same thing. We fit the line, but now the uncertainty in this fit is smaller. So the uncertainty with which we can do a line fit clearly depends on the width of the line, but the uncertainty can be much smaller, and it depends on the signal to noise ratio in your measurement. So a good rough formula for this precision is the precision that you can get is the full width of maximum divided by the signal to noise ratio. The fundamental limit is photon noise. So the signal to noise ratio, if you observe n photons, is the square root of n. So an example for that, it's very widely applicable. This has nothing directly to do with precision radial velocities. This is true for all kinds of measurements. So for instance, positions of stars. If you think about the Gaia satellite, it has a resolution of 0.1 arcsecond, which is typical for a diffraction limited performance of a 1 meter telescope in space, but an astrometric precision of about 20 microarcseconds. So again, if you have a high number of photons, you can get a precision that is much better than the resolution. And if you apply that to Doppler spectroscopy, if you have a resolution of 100,000 and a signal to noise ratio of 100, you get 3 kilometers per second divided by 100. That's 30 meters per second, much better, but still not quite there. So we have to think about the other fact that helps us, and that is stellar spectra have very many spectral lines. And each line provides a statistically independent measurement of the radial velocity. So if you have n lines in your spectrum and you can average over them, you get another factor of square root n. In practice, you wouldn't do that. You would calculate a correlation function, but that's just a technical detail. The intuitive thing is if you say, if you measure 1,000 lines, you gain another factor of square root of 1,000 or about 30, and that gets you down from 30 meters per second to 1 meter per second. So the two things are high signal to noise ratio and many lines. And you can condense this information on the number of lines in a factor that is frequently called Q, that takes into account the wavelength range, the resolution, and the stellar spectrum. And you can plot then this quality factor as a function of the spectral resolution. And in the pre-recorded version of my talk, this is explained in a little bit more detail. And what is important to notice that you typically need a resolution in this region of 100,000 to get the optimum results. There these curves flatten out depending on also the rotational velocity of the star. It doesn't pay off to try to have a resolution that is higher than about the resolution that you just resolve the stellar lines. So now the next thing to consider is the spectrograph stability. And again, talking about very simple things, 1 meter per second corresponds to roughly 1/1000th of a detector pixel, or about 15 nanometers or 30 silicon atoms. So that means we really need extreme instrument stability. We use vacuum to eliminate pressure fluctuations, high thermal stability, typically at the millikelvin level. We have no moving parts in our instruments. We leave them undisturbed, and we calibrate simultaneously. So the overall layout of such an instrument is something like this. Here we have a vacuum tank with a spectrograph inside. We have a front end that's attached to the telescope, so that sends light into fibers. And in this case, there are two fibers. One is fed by calibration light, and the other one carries the light of a star. And in the case of CARMENES, we have two such instruments. Other spectrographs, most other instruments have just one spectrograph. There are some auxiliary systems, but that's the overall layout of such an instrument. What you observe looks like this. Here is the stellar spectrum. You see many stellar lines, and this is an exposure of a calibration lamp. And you remember, the task is now to measure the shift between those two spectra with a precision of 1/1000th of a pixel. And we do this simultaneous calibration because it's virtually impossible to build an instrument that is so stable that the spectrum wouldn't move on the detector. Yeah? 15 nanometers is a tolerance that is just unrealistic. But now we place two fibers side by side and we record the light simultaneously. So we only have to measure the difference between the two fibers. And most of the instrumental errors move both fibers in the same way. And that gives us typically maybe a factor of 30 or 100 or so of improvement. So the total spectrum may shift by, say, a few meters per second, but the difference between the two fibers then shifts only by a few centimeters per second. That's the idea of this simultaneous measurement. Lamps, hollow cathode lamps, are in principle very nice because the wavelengths provided by these lamps come from atomic physics. They are defined transitions. But the problem of these lamps is that they contain many lines that are useful for your calibration, but also a number of very, very bright lines here, for instance. And those lines almost destroy the whole spectrum. You can see that there are artifacts here extending over the whole instrument. So that's a big problem with these lamps. And therefore, many instruments have adopted a strategy where they use a Febry-Perot etalon. The Febry-Perot etalon is nicer. Oops, that went a bit too quick. The etalon is nicer because here we see the etalon that has equally spaced lines with equal brightness. But the etalon, the wavelengths are set by the separation of two optical plates, which is kind of arbitrary and can drift. So we have to tie this etalon then back to the atomic transitions of a lamp. Another way of doing this, which is in principle better, but also a lot more expensive, is using a laser frequency comb, which also creates a nice regularly spaced lines, but does that directly being tied to an atomic standard. So there are different approaches to this, and there's more details in later talks about the use of these different techniques. Another important consideration is the input stability. The spectrograph itself may be stable. If your input is not stable, then you also have a problem. And to understand that, you should remember that at each wavelength, the spectrograph creates an image of the slit on the detector. And the entrance slit actually is normally not stable because you have seeing and other effects, imperfect guiding of the telescope, so that changes the slit illumination. And with that, the illumination changes, and that looks like a radial velocity variation because the image on the detector shifts. And this is where optical fibers come in. Optical fibers have the nice property of scrambling the light, so the output of a fiber is always more stable than the input of a fiber. This is why almost all of these instruments are fiber coupled. And there are tricks now, like using an octagonal fiber or a scrambler that make the stability even better. So here are some images of a round fiber. Here's the input. We moved a bright source on the input of the fiber. This is the output. This is the near field. This is the far field. So this is directly looking at the fiber. This is looking at the screen at a large distance. And you see that it's not completely uniform because the fiber has this circular symmetry. If you use an octagonal fiber instead, it looks a lot more uniform. So that's one of the possibilities to improve even on the round fiber coupling. I just wanted to remind you that the atmosphere also does bad things like imprinting telluric absorption. That will also be discussed later on. And I finish with this last slide where I have noted the most important problems that we are facing in this field. I quickly covered the basic physics, photo noise, stable spectrographs, stable coupling, and stable and precise calibration. And there will be additional talks now later this week talking about data reduction, the stars themselves, and about the atmosphere. So thanks for your attention. And there's a slightly longer version, of course, on YouTube that you can also look at.
Excellent. Thank you very much, Andreas. Okay, let's get through some questions here. First one, what is the physical meaning of diffraction order M?
Yeah, so the diffraction order M, you go back to this very first so-called grating equation. That is the equation that is the condition for constructive interference between the beams coming from adjacent grooves on the grating. And that is that the wavelength difference between adjacent gratings is an integer number. If you have an integer number of complete wavelengths, you get constructive interference. And that number M, this integer number, that is called the diffraction order.
Okay. So Andrew Mayo has always wondered why an octagonal fiber is good. Why not, for example, hexagonal or decagonal?
That's a practical matter. That's a very good question. There are actually theoretically even better cross sections, like a D shape, for instance. The octagonal is used a lot because it breaks the symmetry of the round fiber, but it is still adopted quite well to the stellar point spread function, which is round. If you take a square, for instance, or hexagonal, which is also very good for scrambling, it is more difficult to couple light efficiently because the point spread function of the telescope is round. There are other architectures in which you, for instance, I think Deborah showed a rectangular fiber that could combine the effect of scrambling and slicing. So you could, then you have a fiber that is already adapted to the entrance of a spectrograph.
Okay, won't image slicers introduce non-uniformity in the spectra compared to a direct fiber feed?
Yes, it's true. You have to take this into account in the data reduction. In the raw data that I showed, it was clear that you can see both of these half moons separately, and you should treat them kind of as separate measurements of the stellar radial velocity. So you have to take care of this, and this is partly a matter of data reduction. Certainly at the 1 meter per second level, this is something we haven't seen any problems with that so far. Maybe it's a bit more of a matter of concern, or you have to be more careful about it if you push to even higher precision. It's certainly something to keep in mind in a careful analysis of your error budgets.
Okay, thank you. How exactly is velocity precision related to pixel number? I guess pixel sampling is the question.
Yes, good question. So the sampling, the rule for sampling is called the Nyquist rule, or it's based on the so-called Nyquist theorem. And that tells you that you need at least 2 measurements or 2 pixels across the profile of a line. And it also tells you that you do not gain very much, or theoretically you don't gain anything by having more pixels across a line. So we always design our instruments such that there are 2-3 pixels across one of these lines, but not more, because if you had more pixels across the profile of a line, you would have additional noise, readout noise of the detector, and you also, of course, would be using up some of your valuable detector real estate for that.